Okay, so we're going to go through hashtables today. We are going to go through the functional stuff because this is going to be part of the next tutorial. If you look at the, should probably get it up. If you look at the tutorial notes on the website, which I'll update mine to reflect this probably sometime, but I don't know, it doesn't really have to. You notice that there's the sorting part, which is already there, as well as and then there's also talking about the practice exercises and graphs as well. But there's also this kind of stuff training about selection sort and stuff like that. So we'll go through all that and we'll build all those functions and write all that. But we'll also do all the higher level ordering stuff as well. Well, actually, no, technically there won't be a week 9 tutorial. Oh yeah, because I won't be on one. So I'll make a different video for the week 9 in the event that people don't want to go to another tutorial. So there's a choice. We probably won't need the extra hours, so we'll see how that goes. We can always do a tutorial at the end, but anyway. Let's just begin. Okay, so we're going to go through the fun stuff later, which is all the mapping and this kind of stuff, because this stuff is actually really useful, but it's not part of this tutorial yet. So we can go through week 8 first. So this hash tables, and most importantly, we care about a few questions. These questions are quite important for final exams. So it's probably one of the most, I don't know, this is like at least every exam I've seen typically has a question on hash tables. So it's good to know what they are. So first off, let's talk about what a hash table is. So we know what an array is, right? So an array is obviously just an indexed-based collection between a series of numbers, and you can like store some values within these spaces, right? So an array is effectively like a hash map in some ways, or hash table. They mean the same thing. Hash map and hash table is just a synonym effectively in the industry. And so when we talk about a map, we're just saying, hey, it takes some kind of input, like an integer, and returns a result. Like, I don't know, maybe like a structure, right? Or it could return another integer or something else, right? So it could return, I don't know, let's say a string, so a character pointer, right? And for the sake of it, I won't use mathematical definition. I'll use the definition you used to. So it's taking some kind of integer and it's returning some kind of character. That's a standard array. So if we have an array of strings, that's really what's happening, right? So we have some kind of input, like you have a string here like hey, and you give 0 and it gives you back hey. Now, a hash table basically goes, okay, well, can we replicate this behavior? But instead of requiring this always to be an int, can we use something else? That's effectively what we're using it for. Now, we know a few ways that we can do this. The first way is when you're saying called, a binary search tree, right? And so we're basically getting the same behavior. We're giving a key of some sort. It doesn't always have to be an integer, right? We can give a string key, as you saw in your first assignment, or we can give many different keys. And they're giving us like various results. Like, for example, in your first assignment, you returned a TF-IDF, right? And in this assignment too, I think you do have to do a BST for the second part. So effectively, this is one way. This is, obviously the other way. A linked list would be like another way, but with a linked list, it's not very efficient. It's on, right? Because you have to search through the entire thing. This one's going to be like O log n. This one's going to be sometimes on and sometimes O log n. It's O log n if sorted, right? If it's sorted, we can do binary search over it. So it's effectively just a BST, but like contiguous. And a hash table goes, okay, we want a function that takes in our type, and we call this typically our hash function, right? And this hash function takes in any object, right? But we have to build a unique hash function for each object. So let's say it takes my character pointer, and it's going to return back an integer. And we can use this integer as an index. That's all a hash function basically does. Now, if we think about it a little bit more abstractly, we can think about, okay, if we have a hash of x, and let's say this is our x, right? And in this case, maybe our hash function is going to map. I'm going to give this like a little subscript just to make it easier. If this one's going to map just integers to integers, it just makes it easier for this example, obviously, because you can't really do strings across an axis. But if it's going to map integers to integers, right, we got a few different definitions. Let's say our first definition is going to be, actually I'll just do lines for this. So our first definition, which is hash1, is just going to equal 5. So regardless of our input, it's always going to give us 5. Now this is a pretty terrible hash function because it's going to look something like this. Right? Actually, let me do different colors. Yay. It's like this, right? It's straight line. Now let's build another hash function. This hash function is going to take our input. It's going to do some arithmetic to it, and I'm actually going to steal a hash function from here. Mod 11 will be fine. It's not going to be great, but it'll be better. Right? Well, actually, even mod 11 isn't great because how big is our table? Because it's really just wrapping around a table. Like mod 11 isn't actually going to make that much of a difference. Because then we're just going to multiply by a table size. I've got a better hash algorithm somewhere here. Here, 3891. That's okay. You know what? It's fine. We'll just do mod 11. Mod 11's fine. So mod 11 means that we'll just do some integers here, just to make it easier. So we have 0 to 11, right? And this is just going to look like a straight line. It's like not going to affect this whatsoever. Then as soon as we reach 12, it's then going to reset. It's kind of a bit awkward to do, but effectively it's going to reset down here and then just continue. This is filled in. And then reset down here and continue and so on, right? And so what we actually want a hash function to look like, and it is actually going to go up to 11. So we'll put 11 up here and it's going to go up to like here-ish. It's kind of awful, but you get the point. Let's do each of these lines. Okay. This one and 11 we can put up here. So it's going to go up like this, right? You get the point. Like it resets at every 11. This is 12, and this will be at like 22 or 24 technically, right? Or rather, it's going to reset at 24. Well, actually, no, we'll reset at 23. Anyway, because we're going to be adding 11 each time. So even that's wrong. It's going to reset at 11. Oh my gosh. This is not great. Start. Let's fix this up. Okay. It's going to reset at 11 and it's going to reset then at 22. I can't do modulus in my head apparently. But yeah, so because obviously modulus 11 mod 11 is going to be 0. Alright. Okay. So continuing on, that's an okay hash function, right? And we can call this hash function too, right? Our best hash function though is going to be a hash function that is monotonically increasing and never resets effectively, right? So really it can be any type, we could do even something like this, like just x, right? Obviously for an integer, this is the best hash function, which sounds crazy, right? But basically what you want for a hash function is you want it to be equally distributed. Right? So you want it so that all the values have an equal distance between them, or not necessarily equal distance between them, but each value has an equal equivalency and that there's no overlap. No overlap is the important part. This is practically impossible, right? For most things. Some things it's possible to build a hash function, but even if you get a correct hash function, as we'll see in a moment, it doesn't actually matter because the problem is that even if you may have a perfect equally distributed set, you still get collisions and you still get overlaps when you try to fit them into a table of a specific size. And this is okay. Hash collisions are okay. And this is where the approximate performance comes in. So we often talk about hash algorithms, and when we talk about hash algorithms, we say that they're O1, but more importantly, we do this little weird thing here. Right? Now I'll draw it better. So what we do is we do this. Now this is a theta, which is typically used for like angles, but in this case, it's used as like an average. Right? So it means that the average complexity is O1, basically, right? And this is because if there's no overlaps whatsoever, if there's no collisions, everything gets, its unique value in the array like this, then it's just O1 to grab it, right? We just have to hash it, and then we just get it. It's easy. If there are collisions, and there's various different ways we can handle collisions, then once we visit a node, we may have to perform a certain amount of action. And the problem about all these actions are worst case ON. So actually a hash algorithm or a hash table is worst case ON, average case theta 1, or I think it's actually a term for this. I just always call it theta 1. And yeah, so it's kind of weird. It's like, it's not necessarily always better, but it's never worse, right? And it's often better, or an average better. So let's actually look at the question. So there's two cases. So the first case is obviously the best case is when there's no collisions, which I just mentioned, and the worst case is when there are collisions. So let's talk about if there's collisions. So let's say we're trying to fill a bunch of numbers in, and all we do is we keep giving you 1. So this is all we give you, like a hash function, right? Hash of anything equals 1. So what's going to happen is we're going to try to insert the first element into the slot. Let's say we try to insert 0 into the slot. There it goes. Now, there's a few ways we can do it. It doesn't actually matter what way we do. Regardless of what way we do, we're still going to end up with an ON complexity. So the first way would be, or worst case ON, the first case would be if we try to do linear chaining, or chaining. Right? I call it linear chaining for some reason. It's just a habit. It's because it's a linear linked list, I guess. And so it would look something like this. Everything has a hash of 1. Everything has a hash of 1, right? So it's all going to go into this first index. Right? This is 0, 1, 2, 3, 4, right? And so if I want to find 3, I get the hash instantly, or O1, and then I have to search through n elements to get to 3. So the complexity of that's going to be ON. Other method. Right? The other method is linear probing, basically, or probing. We basically just look for the next free slot. So in this case, we're going to look this way, and then we're going to wrap back around to the beginning. So we look, okay, there's a free slot, there's a free slot, there's a free slot, wrap back around, and stop here, right? Now, tables automatically, just like graphs, they store the number of, they store n, which basically means like the number of values, and they also store, so typically they store 2 things. They store size and capacity. So capacity is like the maximum size that they could fill. So in this case, the capacity is 5 and the size is 5. If I added 2 more elements, the capacity would be 7 and the size would be 5. And then once these are the same and you try to add another element, it will extend the hash map first. So always make sure there's always enough room. There's never going to be cases where there's not, right? I guess if it failed to resize, it would probably give you back some kind of error. Depends. And so in this case, if I want to find 4, I've got to go, okay, I start off at 0 because the hash gives me this value. This is not correct. Okay, go to the next one. Not correct, go to the next one. Go to the next one. Wrap back around. And I finally found it, right? So that's n elements to go through. And the final case is double hashing, which is basically where what you do is you provide another hash function, and that hash function changes over an iteration. So effectively, it looks something like this, right? And so what you do is, I've got an example here of a double hashing algorithm, like this. So you go, position equals my first hash of my key plus I times my second hash of my key, right? And then I mod this by the table length. We're not going to be worrying about that right now. I will do it anyway because it's useful, but don't worry about it. The reason why we mod it by the table length, and I'll go for this in a second, is just so it wraps back around, right? And you see that this happens for every hash. We always mod the hash by the table length, always, because it means it wraps back around. So if our hash value gives us, like, let's say, 1,000, and we only have 10 items in our array, obviously our maximum index is 9, right? And so if we have only 10 length, this is our max index. And so what we want to do is we want to get a value between 0 and 9. So what we do is we mod it by 10. So we go, 10,000 mod by 10, and that's going to give us 0, right? Awesome. Okay, let's just erase this. So let's continue. So we have this while loop, and this is just going to go while position is some valid thing, right? It's valid, or some sort. Like you look inside your hash map and see here. So while there's a collision, sorry, I shouldn't say is valid, I should say isn't. You want to stop once it is, right? And then all you're going to do is you can go like I++, right? So you can set like ID 0, you don't care what position is, right? And typically we use what you'll see here is I used up here, I use an uint64t. It's just because we don't really want our hash functions to return us a negative number because there's no such thing as a negative index. So we make them unsigned, right? And often we want them to be pretty large, so we make them the size of whatever your computer is. So the simplest way is to make it like a uint64, which means it's an unsigned integer that's of size 64 bits. It's typically the pattern that we use. And you can see here, I've got a typical case and a very simple hash function, which is not a great hash function, but it's a hash function. And this cast may seem weird, but it's okay. Because it'll just, if it's negative, it'll just become very, very large, and that's fine. We don't really care about the values. We just care about everyone having a unique value, or mostly unique. Alright, so in this case, we have this hash function. What will happen is if this will hash over and over again. So if our hash2 is just equal to 1, right? This is very bad hash, but it's a hash value. The only thing hash2 can't be, hash2 can never be 0. That's it. It really can be anything else. I talk about it down here, maybe. Probably somewhere. I don't know. Apparently I don't. Yeah, I don't, but yeah, the only thing it can be is not 0. Oh yeah, here, I say here, right? So they can't evaluate to 0, and they have to ensure that all positions are eventually searched. So I guess that means they also can't be a even number, because it means that if your table size is even, you won't search all elements. So basically, they typically have to be odd, typically, I guess, and have to make sure that all elements are searched. Actually, no, that's not true, because if you, well, yeah, that is true. Even number times anything will always give you even. Yeah, okay. Yeah, so anyway, they basically have to make sure all elements are searched and not be 0, right? So obviously, if it's 0, it's just going to do nothing, right? So in this case, we do the same thing. It's going to be 0. And then when we try and insert the next element, in this case, it's basically going to become like linear probing. So if we change this to use 2, which is okay because our table is of size 5, so it's fine. I guess we could even set to 3 and make it always fine. So what we'll do is we'll do 0, or in this case 1, and then it will add 3 to it. So it goes, okay, there's already, when I want to insert 1 here, I can't because there's already a spot here. So I'm going to go 1 plus 1 times 3. So that's going to give me 4. So 0, 1, 2, 0, 1, 2, 3, 4. Here I am. And then I add another 4, so that's going to give me 7. That wraps around to become 2. So here. Again, that's going to give me 10. That's going to wrap around to become 0. And then eventually, the next one will wrap around and may take multiple times to wrap around until finally it will land on 4. Or 3 in this case, actually. But the value will be 4. And so that will be double hashing, right? And so you can see how that worst case is ON, because we have to go through worst case. This will have to be n times the number of keys in the element size, right? We'll have to try this n times. So typically double hashing is the best from what I've seen in terms of performance out there. It's really, make your own judgment. It depends on what scenario you're using. The easiest is definitely linear probing. So if you're going to have to write one in an exam, which you probably won't, then I definitely recommend using linear probing. It's just much, much easier. Linear chaining is probably one of the hardest ones to write, and it's not that efficient, so it's probably not that good. It's not, it's not particularly easy, right? Because you got to use like linked lists and stuff like that, right? It's a lot more work than just like searching for the list to find an empty element. But who knows? The benefit of linear chaining, though, there's actually a pretty good benefit of it, and the benefit is that you don't use up slots that would have already been used. Actually, I should note this. So, for example, with linear chaining, you're using up the same slot, which means that if your function is really, really well distributed, i.e., you're using like integers, then linear chaining is often more preferred because your numbers are so much more distributed. The likelihood of collisions is already pretty low. And so in those cases, when you use things like double hashing and linear probing, you're filling up other slots, which basically means that collisions in the future are more likely. So these are what we call, like, I guess you can call them degenerate in terms of that they become worse over time, right? I don't know, many ways you can call it. And so they're going to perform worse and worse and worse and worse over time because more and more slots will be filled. So basically, as soon as you, if you're more than, let's say, 80% filled, then they're going to perform potentially worse than linear chaining because this will have less items filled, right? Less slots filled because when it collides, it just adds it to the same slot. So I'm sure there's some performance analysis that show that these things are that linear chaining is pretty good as well, but I don't really like linked lists in most cases. I find them pretty inefficient, so I typically prefer not using them. Yeah, so what they want is they want just to do this hash function here. How long have we been doing this for? 3 minutes, that's fine. I will quickly do it, but really that's kind of the rough estimate here. This is a simple hash function for strings. You can hash in your assignment. I wouldn't really I wouldn't really recommend it. But one of the things that you'll notice is that if you use an adjacency matrix, you need some way to convert the strings to indices. And hash tables are really good at converting strings to indices, right? So you could literally just like sit a hash table on top of your, and this is actually something that happens in somewhat real life, is that, if you have an adjacency matrix that looks something like this, right? And then you have, your columns here, and so on, right? Okay, I'm going to change this. Just do this, right? You kind of get a rough idea. So we got these kind of like rows and columns, right? Now we could say that these are the twos. So this is our froms and this is our twos, right? When we want to get an index for either of these two, right? Because obviously we want to be able to convert back and forward. What we can do is we can basically have a hash function that takes our string and that outputs an index, right? And then we can mod it by the total size of the thing, like that. And this will give us something between this and this. You have to obviously handle collisions, right? Because collisions could occur, and you probably want some way to go back. Probably you don't really care about going back, I don't think, but you probably do want to think of some way to go back. The easiest way to go back is to basically just store more than just an int in each position. So instead of something like this, you could store like a slot in that position instead. So it would be like, I don't know, something like this. And the slot would be some kind of structure, which would contain the weight, as well as maybe containing something like character pointers or something, right? There's various ways you could do it too. You probably don't need to be able to go backwards, but that is a downside of using hash tables, is that they're pretty tricky to go backwards because you don't, unless you're actually storing the keys on the specific positions, it's pretty tricky. The other problem is that you actually have to store what keys in which position, so this can't just store an integer. It would have to actually store some kind of slot anyway. But yeah, anyway, you don't have to do it for your assignment, but there's a way you could solve it. Typically, we always use prime numbers for hashing. That's the only other thing that I care about, really. And I'm just going to grab this table, and then we can look at a few cases of it. I'm just going to do a few of them because I think most of them are pretty straightforward. Okay. Oops. Grab the pointer, and we can just do a hash function here. I'm just going to do like a column line here. Wonderful. Okay. Let's look at this. This is our table. You know what? I don't want to do that. As soon as I did it, I was like, you know what? I don't actually want to do it that way. But it's going to change it slightly. We're just going to do it a really quick table. How big is the table? They tell us it's going to be, insert the following into what table? If I don't say. We're modding it by 3 for our second hash function, but we're using 11, so it means it's going to be a size of 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And I'll put indices. Alright. Okay. So our first one is going to be 11. It's got a hash of 0, so we're just going to chuck in the 0 slot here as 11, right? The next one's going to be 16, which is going to go in the 5th slot, as you can see here. But it's going to use linear. We're going to use linear chaining here, or chaining, and yeah, so on. 27 has the same hash function, so it goes down here. All right. 35 has a value of this, right? And as you can see, what I'm doing, I'm basically, this is what you have to do in an exam. You read, or you calculate the hash functions. You probably won't be given all of these. You'll probably just be given the top numbers and what function to use. So you'll just be given these and, you know, obviously the keys. But you won't actually be given these. These won't be given to you because you'll be expected to be able to calculate those yourself, typically. So the strategy is obviously to probably start off by writing all the function results, you know, writing all these down. Then once you've written them down, it's literally just one by one, go left to right, and you just look at the value. So we see 0, we add it here. We see 5, we add it here. We see 5 again, and we go, okay, we can't add it here, so we choose our collision method. In this case, we're using, you know, chaining. And chaining basically means that we have to chain them after each other like a list, right? As I said before, so we're just going to chain them. Then 35 goes here, 22 gets chained, 20 gets added, 15 gets 4, and so on, right? Just keep going all the way through. Now, if we're doing another method, which is in this case going to be, okay, so up to here, so 27. So let's choose our second method, and we're going to do probing. We're just going to add it immediately after, just like that. So 35 goes here, 22 goes here, 20 goes here, 15 goes here, 24 goes here, but now it goes here. And you can see how we're filling up much more slots. So these slots here were used to all not be filled before, but now they are. And so that filling up those slots means that if we get a 1, or we get a 3, or we get a 6, we're going to end up with another collision that we wouldn't have had before. So as I said before, these make things worse in the long run, right? But typically when you resize your table, you have to like rehash everything. So typically that means that things get distributed nicely, and so that kind of fixes things. So it's typically not as bad as it sounds in reality, and it is much nicer to your computer when you do something like this, because you don't have all these pointers that point out everywhere, which means that all the memory is really close, and we love it when the memory is close because the computer can just load everything up at once. The next method is double hashing. So we basically look at the second hash and we go, you know, 5, in this case, 5 plus 1, and we go 5. If that doesn't work, then we try 5 plus 2, then 5 plus 3, and so on. So we just keep adding this second hash, but multiplying it by an increasing factor every time. So in this case, we're going to add just 1 to begin with. So 27 just goes here. 35 goes here. There's no collisions. That counts up to 5. There we go. 22 would normally go here. It doesn't work, so we add 2. But you notice, if we add 2, we get another collision here. Oh no, so we add 2 again, right? Or we add 2 times 2, I guess, right? So now we can fit it here. And then we go to 20, no collisions, good. 15 goes normally to 4, but there's a collision here. Oh no. right? Why is that collision? Oh yeah, because of this. See how this jumped twice? So it used to be 0, but we added 0 plus 2 plus 2, which means now it's here, which means that now we've ended up with another collision that we normally, as I said before, wouldn't have had, right? So this now has to collide. And this doesn't mean it's worse, right, than linear chaining, as I said before, right? To kind of repeat this, even though it does seem worse, the fact is that you're still getting the same worst case performance. It's just where you're putting the nodes, right? And if we extend this graph, if we extend this table, let's say by double the size, then everything's going to be distributed more sparsely, which means that all these collisions will go away. For example, this will go away. For example, instead of percent 11, if we did percent 22 or something, let's say, then this would become slot 16, right? And this would become slot, well, I guess 22 would be 0, 23 would be 1, 2 would be 2, 3. Yeah, I don't know. I'm just going to do math. I don't want to do it. It's too late at night. So 27 mod 22, 5. Okay. Right, and so this would be 16 and this would be 5. It doesn't change. I should have realized that because we're just doubling the modulus, so of course it's just going to be the same. Anyway, so as you can see, that would mean that we wouldn't end up with that collision. So just going to keep going. We just did 35, I think. No, we did 22. We did 20. Did we do 15? Nope. Okay, so we've got to do 15. It doesn't fit in 4. Doesn't fit in 5 because we're adding 1 each time. Doesn't fit in 6, but it fits in 7, so it goes here. All right, and then we have 24, which goes in 2. Doesn't go in 2, so instead it goes in 3. All right, I'll finish this one off because I think this one's a good example. And then 29, instead of going in 7, it has to add 3. So 1, 2, 3. It goes in 10 right here. And then in 19, instead of going, just fit in 8. That's nice. And then 13 tries to fit in 2. It can't, so it goes 2 more to 4, 2 more to 6, 2 more to 8, 2 more to 10, and then back around 2 more to 1. Right? And this is our 13 here. Yeah, right? So you can see all these values are very nice and distributed. And that's the result. And that's what you've given a test, right? So what you typically do is you may have to give every step one by one. They will typically stay. So they'll say, show steps. Or they may just say, show the result. So if they say show result, then you can just say this is the answer here, right? If they say show steps, then you should show the hash map one by one, every change, all the way through. Typically, they may make you do show steps for one of them, and then just show result for the rest. It depends, right? And it will be on typing, so you have to type up a document with tables. You can use vertical bars to do in betweens and so on. Anyway, so I don't know. I guess I can show an example. So it'd be something like 1. So an example would be 1, 2, 3, 4, something like that, right? And so you use vertical bars or whatever you want to use, an or sign to kind of separate them. Anyway, that's enough for this video. I'll probably do one later for functional programming, probably tomorrow or something. And I'll release that in time for the tutorial. Cheers.